So continuing with our previous characterization of, or rather interpretation is a better word, of how we interpret quantum reality, whether it's Copenhagen or whether it's many worldview. Fundamentally, we were engaged with these two ideas. In the first one, the observer creates reality. In the act of measurement, it collapses the state vector collapses to a given value. While in case of the many world view, the state vector is a combination of the measurements, which includes the part in which observer is entangled with what is going to get observed. That's one part of it among the many measurements you can have. But since there are problems in both interpretations, in the sense that once we make a real measurement, we will have it corresponds to a definite value. For example, in a Stern-Gerlach experiment, the state corresponds to a definite value, which can be taken, it can have a correspondence to way we understand how we can identify classical states. So in the act of the end result of measurement in the quantum mechanical systems from these Gerlach experiments, the measurement will assign a particular value after the act of measurement, so which has an analogy to the classical states. So in this context, how can we address the difficulties of these two interpretations? So that's the thing. So whether it's Copenhagen or whether it's many world. So here, this Meinberg has structured it mainly in the binary of this and this. There may be other alternate interpretations also, but since this Copenhagen interpretation, it absorbs the mainstream part of how we do as an practicing physicists. We are doing no. You can sit. You can sit. So that in the Copenhagen interpretation, you can have the reality is basically. So what I was trying to say is that Copenhagen interpretation is a mainstream interpretation of how operational physicists or working physicists mostly work with this interpretation. And physicists like Bohr, Heisenberg, and other people which who study as part of normal textbook literature. But many worldview is another interpretation which is also there if we want to understand the foundational aspects of quantum mechanics really seriously. Okay. Actually, I'm recording this lecture. If you are interested, you can sit. If you are not, it's up to you. Yes. No. So it's up to your choice whether you want to sit here or not. So in these two interpretations, so the point is, so here comes the idea of decoherence. Decoherence means that a system will. So you cannot. So for example, you cannot isolate the way it can have an analogy in thermodynamics. You cannot have an isolated system in that sense. So energy exchange will always be there, even if they may be infinitesimal or they may be tiny in their what I should say exchange. So in that sense, you cannot insulate or isolate a system from its environment. So even the small perturbative changes, whether they affect the system, so that's the point. So the whole point is that there has been this idea of decoherence. So the question is, so what's the, how can we reorient or restate the state vector? So we will not say that even though state vector collapses to psi and psi star, but here the thing is that if we say that perturbations can and do rapidly change phase of classical states. So which means that for example, so if we have a, so if we, it's not in the Schrodinger case, like psi, whether cat is dead or whether it's alive, psi dead. So either once we make an act of measurement, it may be either dead or it may be alive. It will only have choose one state in the Copenhagen interpretation. In the many world interpretation, it will have both these things. In one state, it will have the psi may be alive, but in the other state, the act, the observed measurement will leave it dead. So if so in our case of decoherence, what decoherence does, that it will have a slight change in the phase of a given state, rather than changing a state from either being dead or either being alive. So that's the point. So if, for example, if psi alive plus psi dead can be written as, so if you allow a phase factor of e to the power iota alpha psi alive plus e to the power iota beta psi dead, where alpha and beta are fluctuating phases. So this has been introduced by Juice and Zig. We can see the reference to it. So if you so decoherence will allow change of phases vis-a-vis those states, rather than changing of those states in some fundamental way. So that's it. So as a consequence of decoherence, what will happen is that we had, for example, state of, so we used to write state like this, psi of 0, which is acting on an operator. We used to write it like this. Now, with the presence of this phase, e to the power iota alpha or e to the power iota beta, what we are going to do is that the state, altered state, which accounts for the phase change, which may be due to the environmental change, which incorporates the state into a changed state. So you can have as sigma n exponential of iota phi n Cn psi of n. So you can, so you just see where n can be 1, 2, so on and so forth. So if so this is our state. So this is the phases accounted by this exponential of this factor into consideration. And if you want to calculate the expectation value and the interferences, between different terms in the superpositions, which may average to 0. So the observed expectation value of the Hermitian operator A can be, and this, it can be like this: Cn square, so psi n an It's a psi of an. So here we know it traditionally also it's like that. But here the Cn square it should also what will it be that because we have to take into consideration the phase factors which are involved because when we have environmental the decoherence thing into consideration. Uh, so so otherwise, it's in the Copenhagen interpretation. So the phases arise only because there might be some other features in the system, and the fundamental decoherence or arises. Huh? Uh-huh. So we can say it that. So because in the sense that why we enter into this decoherence function is because we always know that normally we don't deal with closed systems. So even though the system is large, so we in a given system we don't include the rest of the universe in any given dynamical process. So the dynamical process here is how these states psi or they are evolving. They are not only evolving, they are evolving how we are measuring their evolution in space and time, which includes some non-trivialities in our fundamental how we can interpret things or how we can measure things and how or we can account the measurement of those things in a non-contradictory manner or rather in a consistent manner. So the point is that for example, for Weinberg, these interpretations, which include the Copernican interpretation, they remain unsatisfactory. So one of the reasons is that the role of Born rule in this entire thing, because in Born rule we normally know that the sum of probabilities at the end should come out to be 1, and that statement in a sense corresponds to sort of conservation probability, it's a sort of conservation of a given. It corresponds to the way we try to observe conservation of total energy of the system or more. So in that sense, so the point here is that in the Copenhagen interpretation, there may be a mysterious collapse of the system. And if even that collapse will correspond intrinsically to an probabilistic process. So where does a Born rule fit into it? Because the derivation of equation is circular because the formula for the it's the formula for the expectation value of the matrix elements of the operators, which itself derived from the Born rule. So matrix multiple. So how if you just see the earlier sections, how we invoked these. In these operators, they basically were operations of matrices, operators corresponding to those matrices. So this may be ultimately the question is it becomes circular. So we assume Born rule, then we can have this interpretation. But if this interpretation has some problems, so where will it lead to how we get the Born rule? So from this, Here comes the point of how we have the notion of probabilities, which mean much rather the notion of probabilities. So once in classical mechanics we talked in terms of certainties, but in quantum mechanics we talk in terms of probabilities. So, but probabilities for Bohr rule at the end, even that should be come out to be one as a linear combination of states. The total probabilities should come out to be one. But for a system, if it is a system which is not a closed system, or it's an open system, or we don't know the entire system, so the validity of the Bohr rule, how we can get it from the first thing, so it becomes a very questionable exercise. So now, how do we assign probabilities or weight to those measurements? So how we can assign weight to those measurements on those given quantum states. So it's a given problem, and here different interpretations or different physicists they are going to have, they give different value to those weights, or relative weights is rather a better term. And in any book on, if we have a traditional probability, so different how we weigh. So scientists, mathematicians, and philosophers. So they may be the creed of people who have a definite opinion on how they would rather deal with those probabilities. So for scientists, working scientists, they have a different way how they will see the lab parameters, or observational things may be more important for them. For a mathematician, they should correspond to some structures, some how we have those axiomatic way we define those measures, probability measures. And for philosophers, the entire game may just be to how we, as an individual human beings, for them the perception, how it is to be seen, how observer perceives things. So they may not necessarily be whether they are objective or whether they are subject to perceptions. And for a scientist, the data which he is filtering, it's not necessarily, we cannot talk in terms of subjective terms. So the data is it's without you take it as objective. Or so you can have maybe in that context, if I'll only just so there are Bayesian probability system, there's a Keynesian system, there are various ways how we can have different way to these. There's a Janssian. So there are different criteria how we can assign relative weight to these different probabilities. But if we just focus on the book, or rather the probabilities which are more or less taken into consideration, is that what we're going to do, or in physics rather, I'm not, if we just reduce it to physics, we say that probability of observer finding in a combined system in the state psi n an is Cn square. We commonly mean that the observer performs measurement many times. And always starting with the state vector, starting with state psi n A. So expectation value of the observer A is, so if you remember, psi of A psi is basically for a particular observer, it's this. So the sort of interpretation which is more or less is known as the frequentist interpretation of probability, which is how we see a state and its evolution in the system. The way we have a state and the components of the state, how it's given by this inner product divided by this. So this frequentist interpretation is that. So what it basically boils down to is basically we have an interpretation of this frequentist interpretation. So if you want to see Schrodinger equation or time-dependent Schrodinger equation, how the state evolves. So what we are saying is that so if we apply time-dependent Schrodinger equation to the case of repeated measurements. So we are able to derive this frequentist interpretation from applying time-dependent Schrodinger equation to the case of repeated measurements. So we are going to have repeated measurements. So here the point is that if this frequentist once we have in quantum mechanics, we normally have an expectation value, and we basically define expectation value as square of mean minus mean of the square. So how we define it? So it's basically how we average out these repeated measurements around a certain mean or minimum. We just have averaged value of these measurements, or repeated average value of these measurements. So, but if the Born interpretation is suspect, because the Born interpretation is for a closed system, it comes out to be 1, but if you don't know the universe is open or closed, so and how we can have this thing into consideration, so it becomes suspect. So here so both these interpretation, Copenhagen as well as and its many word interpretation, they become inadequate in that sense. So to address those problems, we need probabilities which are tuned to those circumstances. They are fine-tuned to the circumstances or the states in which we are interested in, such that the matter of frequencies of things seen by observers, we have to specify when observer becomes so tangled with the system that we can think of different terms in the state vector as, so we can think of different terms in the state vector as, we can think of different terms in the state vector including different conclusions. So including the different conclusions by the observer. So you can have different terms. So you can see, so the objectivity which we are normally comfortable in general, in science in general, and here in quantum mechanics particular, that objectivity somehow, so you can see, we can think of different terms in the state vector, including different conclusions by the observer. So there may not be a consensus on what a given observer, different conclusions by the observer. So that's it. So it's a if causality is here. So here the causality is the truth as it has been perceived in quantum mechanics. So how? So this can further be accentuated by the fact that, for example, even if, for example, for a case, if we take a system which is if we have an observation and there can be two observations to make this point clear. If we have, for example, if the world splits, into two worlds, or rather, the more comfortable language is of many worlds. If the world branches into two states, if world splits as branches of two states, n splits into n1, n2. The one history in which observer sees the results, for example, and you can have state vector with coefficients which will correspond to these n1 and n2 as c1 and c2. So if we find that the state, observer finds the system the state, or so observer will find the system in the state, either state n1 or in the state 2, state 1 or state 2. So there will be there will be 2 to the power n branches may be there. 2 to the n branches may be there. Which is the so now question is that whether, no matter whether C1 by C2, which are these things, C1 by C2, or either they are neither zero. So C1 and C2 are these associated with these states. The way we have C1, N1, C2, N2, sigma. So the way we so these probabilities which are assigned with these C1 and C2, which are part of this N1 and N2, these states on which this n is broken into. So So either these brush of these probability may tend to 0 or tend to infinity. In both cases, so you cannot able to, you will in these two extreme cases, we will not be able to differentiate the two states or the measurements in the two states. So our conclusions may not disagree. But in case of other states where this ratio of this C1 by C2 may not be necessarily 1 or greater than so or 0, so what will happen? So it will lead to an interpretation which will depend upon the how an observer is going to just filter out events or from the measurement of those states, which is very much subject to and dependent upon the given observer. So if I use read the books, there is nothing in the picture that corresponds to usual assumption of quantum mechanics that assigns probability C1 to a history in which the sequence is founded by the observer. So in a different set of experiments, in a different, so this is how we can articulate some of the difficulties in this frequentist interpretation. Where in the cases where this n1 is now is equal to n2 is equal to 0 or n1 by n2 is very tends to 0 or tends to 0 or go to infinity. So in these cases we may not be able to distinguish the thing for the thing. But otherwise, so now in a different sort of experiment, which is part of those measurement of probabilities, a large number n of copies of the same system are prepared in the same state, which is Cn psi of n, so that the state vector is combined system is the combined system is the direct product of n1, n2, nn, C1, Cn1, Cn2, Cnn, and psi n1, n2, and nn. So if you so where psi n1, n2, nn is a state in which the system S is in state ns. So if psi n is the suitable classical state of the sort which survives decoherence, the inner effect of environment should multiply for each state psi n. So we have a phase factor of exponential of iota phi n by for to this thing. So the interpretation. So if the system, so for closed system, you could say because the probability will be 1, but if the closed system is not there, as the systems normally are, quantum mechanical, if the system is the entire universe, or it's not a system, is a system with some environment, so we have to take into factor the decoherence or how the environment somehow affects the changes in the state, even though they may be tiny. So they will not change the states in the fundamental way. So that's also an assumption, whether small changes will lead to big changes such that they will change the state of the system in a fundamental way. We don't talk of those changes, or we don't assume things will change in that way. If that assumption is left, so those changes will only change the phases of the system, which can be incorporated. That like this, if psi n is n1, n2, nn, so Cn1, n1, Cn2, so on and so forth, exponential of. So these are the phases which are account phi 1, iota phi 2, so on and iota phi n. It's a psi of n1 n2, where phi Sn are random and uncorrelated. So we take the states of this basis to be, we take the states of this to be orthonormal, in the sense that psi of n1 prime, n2 prime, nn prime, n1, n2, and so if we take these phases, so if these are random and uncorrelated. If they are random and uncorrelated, you can just invoke our previous, how we have this inner product of two states. You can write it as n1 prime, n1, n2 prime, n2, so on. So a delta n prime n, n. Such that this probability Cn square is 1. So question is that with by correlating the state this, so if we use the book, if we use, so it's equation 37.9 and it's 37.8. So in this, it's only so microstate system has been prepared in the state this by correlating this with the measuring system and the apparatus. The observer finds herself or himself in the branch of history of the world in which each of the copies of the system is in some distinct definite state. So the observer is going to see himself in a definite state, in some definite basis, which may be in the states n1, n2, so on and so forth. And in which if we have n copies of each states n, then sigma n is n. So probability for a given copy, one copy, is that this is this, n by n total copies. So here is the important point. The point is that, so if there is a subsystem which and there is a system, so the subsystem may be in an evolution, and you may be trying to specify the subsystem vis-a-vis the whole system. So the state psi, the probability of state psi vis-a-vis the whole system. So it's not necessarily that they will be equally, the probabilities will be equally distributed. The random distribution or the average distribution is same in that sense. So even if when we use the law of large numbers, so there may be some problem with that interpretation in that sense. So what's the thing? How we have to do it? So for example, so if we So even in the large n limit, it's not necessarily that average value will be the value of that state which it is corresponds to. So how it and whether it should. So the question is whether it should just ultimately come to this CM square, the whole sum of these probabilities, whether it should come out when we are including these phases. So it's a question. So if it can be better articulated if we just see it the same thing in the sense that in the Schrodinger equation, the second postulate of the quantum mechanics, which says that if a state vector of a system is an eigenstate of Hermitian matter, is an eigenstate of Hermitian operator A, Hermitian operator A, representing some observable, we know it represents some observable with eigenvalue A, then the system definitely has a value A. So eigenvalue it will have a value A for the observable. So where we said that eigenstates correspond to different that value, this thing. So here, so it will somehow contradict this thing so for if the states evolve in that open way, so it will lead to some interpretive problems. So the operators of interest here are maybe the frequency operators. So which will assign a value which the observer is going to choose among the ensemble of those total systems. So, but the thing is that what have we to do it to do the how we can do away with this system. So because now we are dealing not with an isolated system, we are dealing with a combined system. So for a combined system, the probability is psi n1, n2, nm is psi n1, n2, so on. So you can for n by n, if it's infinity of it is 0, the problem is not doesn't arise. For other cases, the problems maybe arise. So what can we do it? So there are two ways of doing it. So if you go to the book, so I'll not so we'll just do it how we have done it. So we'll just try to do it in the coming class.